Hi everyone, here we will discuss one more problem in the rotational dynamics. The problem is if it's given that we have some hemisphere just like given in this way, okay, and it's also given that at the top of the hemisphere the particle is situated. Let me assume that the particle mass is m and the radius of this hemisphere is a units, okay. Now, in case second, what we are going to do, we just release this particle at its topmost position, and what happens to this particle, it will just try to move along this way, and okay. Now in this case, if we need to calculate what's the reaction force that's being imparted by the sphere on this particle, okay, that's what I need to calculate in the case first. Simply here my particle at any instant of time, it will be here, okay, and the reaction force imparted by this hemisphere at this point on this, it will be in this way because it's a type of contact force, and reaction force we just call, it's also known as a normal force, and it's always perpendicular at the point between the contact of the between the two surfaces at the contact, okay. Now this is my normal force here, and obviously the weight of the body, it will going to be aligned in this way, total weight of the body. Now if I will draw the line, it will again represent what we call as the radius of this hemisphere. But if I will just analyze this weight in terms of its components, its one component will be the tangential to it, and one component along will be along this way, okay. And this will be my yes, if this is here theta, this is here the theta angle that made by the particle at any instant when we just release the moment we release the particle from its top at any instant of time. Let me assume that my particle is here, it is going to make an angle theta here with respect to this vertical, okay. If this is my weight here, this will be clearly mg sine of theta, and this will be mg cosine of theta, okay. This will be my theta here as well. Now it's clear from the figure that it will exactly happen to occur. Now if I will analyze here the forces one by one, this is a weight component of the weight of body which helps to move the particle along this trajectory, okay. And this is a normal force imparted by this surface of hemisphere to this particle in this fashion. At the same time, the centrifugal force for this particle motion is because it's a type of curved motion. And if I will just write down my one form of Newton's second law here, what will be that, okay? Means that the first force I will write here, it's a normal force plus, if the particle it will move along this trajectory, obviously it will have some angular velocity omega, okay. And at the same time, we know that how angular velocity of a given particle is related to the linear velocity, and particle velocity is going to this after using some tactical, I mean the right hand thumb rule. What we will get here, we will get the centrifugal force for a given particle is yes A, okay. A is what we call as the type of, it will act as a type of constant equation. The constant equation in this course we have, it will be A is the constant, okay. Now these are the two forces which are going to act on this particle in this way, and there is one more force that's a component of the weight, that's what we call as mg cosine of theta, okay. Or I can say r minus mg cosine of theta plus mv square by a, it will be 0. This will be the Newton's second law of this form, and I will just number this equation first. The another equation I have here right now, when the particle moves along this trajectory, it will obviously have what we call as the particle will possess some torque, because the force acting on a particle at its center, that's this much, and the particle is at a distance of r from this point of analysis here. So this tangent and the radius, they are always perpendicular to each other. If I write my torque, it will be as a mg sine of theta, but my torque will be also, it will can write it as I times alpha. I is the moment of inertia and a is the corresponding angular acceleration. So if I will equate these two equations, what I will get here is, for this particle motion, its angular momentum from this point about this axis, it will be, yes, sorry, it's what we call as the moment of inertia. It will be simply mr square alpha, yes, it will be mg a sine theta, mgr sine theta. Okay, ar, if I write here a, so no issues here are okay. A will cancel here. What I will get, m will cancel here. I will get my a alpha, it is some g is sine theta. Okay, what I need to calculate here, basically I need to calculate the reaction force being important by this sphere on this particle that we just represent by r. This is what I need to calculate here. Okay, so which thing that I need to be know here, if I will write down this equation here once more, it will be yes r plus ma omega square is equal mg cosine theta. Okay, if I will number this equation third, what this equation gives me, it basically simplifies the equation that I wrote down earlier here. Now from here, what I need to calculate, if this omega square is known to me, so I will get this r, but from this equation omega is somewhere higher. So if I will just look for this equation, and I can write it as my alpha will be g by a sine of theta. Okay, I know that the angular acceleration, it will be d omega by dt, it will be g by a sine of theta. Okay, here what I have here is my d omega will be is, it will be g by a sine theta dt. Okay, now here what I will do here, I will just do here one more thing, that I will multiply this equation by yes 2 omega d omega. Here it will be yes 2 omega d omega dt. I just multiply this equation by both sides, 2 omega dt. Here I will have yes g by a sine theta dt. Okay, yes, what I got here, if I will put this dt here for a moment, I will have here dt d omega by dt, that's an angular acceleration, and I have here dt omega. Okay, so what I will get here, 2 omega alpha dt, it will be g by a omega sine theta dt. Okay, now how I can solve this equation, because it will help me in order to solve this equation. By this way I will get here omega square, that I will plug here, and by this way I will get the value of this normal force. So the further calculation here tells me here, if I will just write the equation, last equation here once more, that's 2 omega is alpha dt, it will be as 2g omega a sine theta dt. And this alpha here, yes, it is d omega by dt. Here is dt. I will 2g omega a, yes, sine theta dt, or I can write it as 2g by a sine theta d omega by dt. So this will cancel with this, and there is a dt, it will cancel with this. What I will get here, 2 omega, yes, it's not here, so it's d omega, okay, and it's here 2g a, it's not d omega, it's d theta, because we define the omega is d theta over dt, sine theta d theta. If I will just integrate it, after integrating, what I will get here is, yes, 0 to omega, here it will be 0 to theta, it is d theta here. Now it will be 2 omega square by 2, it will be 2g by a, yes, it will be, after doing, I will just skip here one more step. So after integrating it, I will get this thing, and this will go, my omega square is here 2g by a 1 minus cosine of theta. Now if I will remind the equation here that I write down earlier, that r will be, yes, r minus mg cosine of theta plus m r omega square, it will be 0. So it will be r minus mg cos of theta plus, yes, mg, here it is a, ma omega square will be 2g by a 1 minus cos of theta. So this a will cancel here, it will be minus mg cos of theta plus 2mg minus 2mg cos of theta. Okay, so this is basically minus 3mg cos of theta plus 2mg. So my r will be equal to here, yes, it will be, after doing here the further maths, I will get my r simply here, yes, it will be mg, yes, 3mg is here, it will be 3 cos of theta minus 2. Okay, this is my normal force that's being imparted by the sphere on the particle. Now if it is also given in a question, calculate the value of theta when the particle, it will leave the surface. What I mean to see here, simply I need to calculate this value of, at what value of theta, at what value of this angular coordinate, so that the particle will leave the surface. When the particle will leave the surface, we know that the normal force will be 0, because normal force is a type of contact force, so there remains no further contact between the surface and the particle, and this normal force will vanish. When this normal force will vanish, what we will get here, yes, we'll put r is equal to 0, mg 3 cos theta minus 2, so it will be 3 cos theta will be equal to 2, cos theta will be equal to 2 by 3, and theta will be equal to, yes, cos inverse of 2 by 3. This is the value of theta at which particle will leave the contact with the surface of the hemisphere. Okay, by this way the problem ends. We got the value of the theta as well. This value of theta, it's a representative of that value when the particle will leave the surface. Okay, and this is a type of normal force exerted by the surface of this hemisphere on this particle. Okay, thank you.